Module 7 is on applications, or rather, setting up of the word problems. This is a big part of the calculus topic of optimization, and it comes after the development of all the calculus tools, and then talks about how to actually apply them to real specific modeling situations. We will talk about a variety of different types of word problems in this section, working with various shapes, three-dimensional as well as two-dimensional, right angle triangles, and trigonometric word problems as well. The general approach that we will take is the exact same one as you would take in calculus, and in fact what we will do in most of these problems is set up the problem to get it ready for applications of calculus. The next steps are going to be purely calculus techniques. The general approach is to begin by sketching a diagram, which will help you identify all the given quantities and also assign variables to all the unknowns. We will then have to figure out some equations that connect your variables between each other if there's more than one, and set up the necessary function as required. This is usually the function that in calculus you will be asked to find the minimum or the maximum of. So let's start with the most standard application problem, that of a rectangular field. We are given that the perimeter of a rectangular field is 100 meters and that the length of the field is 6 times larger than the width. What are the dimensions of the field? So, as per guidelines above, first of all, let's sketch a diagram. A rectangular field means that I'm sketching a rectangle that has clearly length and width. I know that the perimeter is 100 meters, so let me record that fact. Perimeter is the amount of fencing, if you think of that as a pen, that is required to enclose this area, right? So the perimeter is going to be all the length of all the sides all the way around. Now, I also know that the length of the field is 6 times larger than the width. So I can assign a variable to one of them and express the other dimension in terms of the first one. So for example, if I know that the width is x, then what is given to me is that the length is 6 times larger. So the width is then 6x. Now I can use my variable x, that I happen to have only one of, to express the perimeter. So here I have to figure out how many x's does it take to go all the way around. I'm going to have x plus 6x for the sides that I already have labeled, so x plus 6x. And then for the other two sides, I'm going to have another x and another 6x. All the way around means I have to add all of them up, and that is what forms my perimeter. Now, this problem does not require setting up of the function. That's going to be done in the next problem as a next step. Here, it's simply asking what are the dimensions of the field. Notice that I've ended up with an equation with only one variable, so I can in fact solve it for x. So on the left-hand side here I have 100, and on the right-hand side, if I bring up all the similar terms, I have 14x. Dividing through by 14, I get that x is approximately 7.14. I also want to draw your attention that this is not yet the answer. The answer is going to be the one to the question, what are the dimensions of the field? So the width and the length. So far we found x, which denoted our width, and now I need to find the length, which was represented by 6x, which in this case will come out to be approximately 42.8. So the length of the field is 42.8 meters, and the width of the field is 77.14 meters. You can of course then check that twice this plus twice that will in fact result in the perimeter of 100. Paul wants to build a rectangular pen for his chickens alongside his house. He only has 30 meters of fencing available. We're asked to set up a function representing the pen's area in terms of only one variable. So this question is similar to the previous one in terms of setup. It uses the same shape, but is more calculus-like in nature because we're asked to set up a particular function, not solve for something. And then this function is the quantity we will actually apply calculus tools to maximize or minimize later in your calculus course. So as before, let's first sketch a picture of what the scenario is. So he wants to build a rectangular pen alongside his house. So let's draw the house wall here. This is Paul's house. and he wants to build a pen alongside it, which means that he only actually needs to build 3 walls, not all 4, because the house wall will replace the 4th wall. What are we given here? He has 30 meters of fencing, which means that all the way around this pen of his, this new fencing, he has 30 meters to spare. So this is kind of like the perimeter, but only of 3 sides. And the perimeter that he has is 30 meters. We're asked to set up a function representing the pen's area. So area is what we will eventually be after. Okay? Now, taking a step back and seeing what it is that we have and what it is that we want, we would like to assign some kinds of variables to this problem in order to be able to describe our given and wanted quantities in terms of those variables. Because this problem is similar to before, it's fairly obvious that a rectangle is best described using its dimensions, so length and width. So here I can immediately assign the variables of length and of width. You can call your variables any letters you like. I am using descriptive names here. Okay? And then I'm going to rewrite the perimeter in terms of my newly introduced variables. So it's the amount of fencing he has available, so that means that W plus L plus W has to be 30, or 2W plus L. So this 30 is equal to 2W plus L. Now, what about the wanted quantity, or my area? Well, I am looking at the area of this rectangle, and that's where you got to be careful. Area of a rectangle is always width times length. Okay, so this is going to be the biggest difference between the perimeter. Perimeter counts every occurrence of W. The area will only count one dimension times the other dimension. So the area here will be width times length. Now, this is where this last constraint comes in. I have to set up a function representing the pen's area in terms of only one variable. And this is key in calculus because we can only find maximum or minimum of the function using calculus tools if the function is written in terms of only one variable. So here I'm not quite there yet because my area function is utilizing W and L. But I can use this equation to solve for one of the variables and therefore eliminate it from the area formula. Notice that this equation is fairly simple, and I can choose to solve for either W or L with the same amount of effort. I'm going to choose to solve for L because it doesn't have any coefficients in front of it. So from here, I have that L is equal to 30 minus 2W, and this is the formula that I'm going to replace the value for L with in my area representation. Okay, so I'm going to plug that in, and what am I going to get? I'm going to get W times L, except for L is 30 minus 2W. And we're done here. I have the function representing the area in terms of one variable only. This variable is the width of the chicken coop. It could have been the length, but I chose the width. So this is my final answer. Let's take a look at the next problem, which is again similar in nature, but builds up on the previous ideas we've just discussed. Seth has 100 meters of fencing to build 2 pens, a square one for his pygmy goats and a circular one for his miniature pigs. Set up a function for the total combined area in terms of one variable only, right? So notice this constraint again, that your final answer has to be in terms of only one variable. And that again is in the preview of calculus because that's the function that you will be able to then apply calculus tools on. As before, let's draw a little picture. So we have 2 pens, a square one and a circular one. So let's draw ourselves a little square pen and a little circular one. What we have here is that Seth has 100 meters of fencing for both of them. So once again, the perimeter or the length of his fencing is going to be 100. And we are asked to set up the function for the total combined area of both of the pens here. Okay, so the area function is again what I am after. Okay. Now, let's introduce some variables to be able to describe both of these quantities. I have a square here, and square is fully described by the length of one side. As opposed to the rectangle, the square has all sides are equal, and so I only need to assign one variable. Let me call it x. Okay, so this x is the length of every side. A parameter that describes a circle well is its radius. So I'm going to use the radius as the dimension of the circle here. And now that I have that, I'm going to use these variables to write down what my total perimeter is, and then to write down what my total area is. One word of caution here: every time I give this problem to students, everybody makes a very incorrect assumption that these 100 meters were split between the two pens evenly. So this pen got 50 meters and this pen got 50 meters. This is not stated anywhere in the problem, so be careful about not making the assumptions that you are not told are going to be present here. It says I have 100 meters in total, so I can make a really tiny little square and a giant circle if that benefits me, or the other way around. Okay, so the total perimeter has to be 100 meters, and that means it's going to have to be the perimeter of a square, which is all the way around. So 4 sides, each of length x, is 4x, plus the perimeter of the circle. The perimeter of the circle, or the fencing that one would need to build a circle with, is the length of the circumference, 2 pi r. Okay, so let me just annotate this a little bit by making it very clear that this is the perimeter of the square, and the second one is the perimeter of the circle. Now I have to do the exact same thing, but for the total combined area, which means that I have to add up the area of the square. The area of the square is length times width, which means x times x, or x squared, which is where the power actually gets its name, times plus the area of the circle. The area of the circle is pi r squared. Okay, so let me annotate this here. This is the area of the square, and this is the area of the circle. And of course, to get the total combined area, I am adding the two. Excellent. Now I am up against this last constraint, that my area has to be in terms of one variable only. Here I have x and I have r. So I'm going to have to get rid of one of them. My equation for the perimeter gives me a way to solve for x or r, whichever way I decide to. Again, here they're both to power 1, so it's a linear equation for both x and r, so it's my choice what to solve for. Let's say I decide to solve for x from here. So from here, solving for x, I'm going to get 100 minus 2 pi r, all divided by 4. Okay, and once I have that, I can plug this expression for x into here to replace the whole thing. So what I'm going to get in the end is going to be this whole expression squared. This used to be x and is now replaced with this expression, plus pi r squared. Okay, so let me just make a note here that this is x. And now I'm done. I have the expression for the area, for the total combined area, written fully in terms of one variable, namely r, the radius of the circle. This structure is very common to many calculus optimization problems, where you have what we call a secondary equation, so the equation that connects your variables, and you have a function that you need to set up that you first will get in terms of two variables, and then you'll need to use your equation to solve for one of them to get the final result to be only in terms of one variable. Some questions are going to be like that, some others will produce a different kind of function, so we'll see a variety of different types of setups in this module. Let's take a look at the next one. Very standard calculus question, a Norman window question. A Norman window has a shape of two squares, one on top of the other, surmounted by a semicircle. Express the perimeter and area of the window as a function of its width. So here we're told specifically what it needs to be a function of, as opposed to before when we had a choice to what to assign our variables and which one to eventually solve for. As before, let's just draw a picture. So a Norman window has a shape of two squares, one square, two squares, surmounted by a semicircle. So my semicircle is not going to be quite as perfect, but there we go, not so bad. Express the perimeter and the area of the window. So here I'm actually asked to express both of these quantities in terms or as a function of its width. So the variable here is given to me, the width of the square. Okay, so let's go through and make sure we can actually label the entire picture with our given variable. Now these guys are squares, which means that all sides are equal, so this will also be all width. So will this length right here. Now from the previous example, we note that the one quantity, one dimension that represents the circle well is the radius. So here it's useful to think about the radius of the circle, or this quantity right here. So note that if this whole thing is w, then this whole thing is w, which means that the radius here will be w divided by 2. All right. So now let's think about the things that we actually have to come up with. The perimeter. So the perimeter is all the way around, which means that I have to think about what it will take to go around this entire square. Okay, so we can see that it's a whole bunch of w's and then half a half circle of a radius w over 2. So how many w's did I need? 1, 2, 3, 4, 5 w's. So this will be my first contribution to the perimeter, plus the length around this semicircle. So remember that the circumference of the entire circle of radius r is 2 pi r. So here it's going to be 2 pi, and then my radius is w over 2. So this is my 2 pi r. This would have been the length of the entire circumference of the circle had it been full. But I only have half a circle here, so I have to divide that by 2 one more time in order to only get half the circle contribution. I can simplify this expression, of course, but I'm not going to bother. I'm going to leave it in this form because it's more clear here where all of these numbers come from. And maybe let me label this. This is the radius of my semicircle. And this comes from the fact that it's a semicircle and not the entire circle. Using similar logic, let's think about the area. So the area consists of 2 squares. Each square will be of area w, so w squared, so 2w squared. 1w squared for this circle, 1w squared for this circle. And then I also need the area of the semicircle here of radius w over 2. So remember that the radius of a circle is pi r squared. Now here I have the radius as w over 2, and I only need half a circle worth of area, so I'm going to have to divide this by 2. Okay, so my descriptions here will be the same. This is the radius of my circle, and this divided by 2 comes from the fact that I only needed a semicircle worth of area. Okay, so notice that the structure for this question was a little bit different. We didn't have to solve for any variables. We only had one variable to begin with, and it was actually given to us. So some questions are like that. Let's take a look at the next one. This is our first one of three-dimensional shape, and it is a cylinder. This is also a very standard calculus question. You want to make a cylindrical can of volume 100 cubic centimeters. We want to express the surface area, not including the top and bottom, as the function of a radius. So once again, we're actually given what we want to express it in terms of, radius, but that doesn't mean that we won't have any other variables either. So let's draw a little cylinder here, just to be able to once again visualize what this whole thing would look like. The cylinder kind of looks like a pop can, which is how this question is generally stated. And the reason we want to express the surface area is because that's the amount of material that will go into making an aluminum pop can. So what I know is that the volume is 100 cubic centimeters. So let me note that volume is equal to 100. And what I want to know is the surface area not including the top and bottom. So only this lateral, the sides area. Okay, so surface area here is what I am after. Excellent. So now let's think about the volume and the surface area of a cylinder. These are probably not the things that you sort of remember from the top of your head, but as you do more and more calculus questions, the cylinder is one of the useful shapes to write down the different volume and surface area calculations for. The two dimensions of a cylinder that are useful are the radius, or that describe the cylinder completely, are radius and height. The volume of the cylinder is then pi r squared h. The way to think about this is, look, it's pi r squared, which is the area of a circle, right? Of radius r. So it's the area of this circle, and it's multiplied by h. So it's kind of like you have these circles stacked up on top of each other h times. And that's what gives you the volume of the cylinder. The surface area, cylinders are kind of interesting shapes, because if you think about this, you can actually fold a piece of paper this way to experiment with it. If you cut the cylinder along one of the sides and unroll this thing out, what you notice is that you will actually get a perfect rectangle. It's going to be of one side length h, because that's how you cut along it, and the other side will come from the circumference of the circle, so 2 pi r, which makes the surface area easier to calculate, because now it's just a rectangle, and an area of a rectangle is length times width. So the area, or the surface area of the cylinder, not including the top and bottom, is going to be 2 pi r h. Now note here, the last step, I need to express the surface area as the function of a radius. So radius is the only thing I'm allowed to have in my final expression, which means that I'm going to take this equation, solve this for the other variable, which is h, and then substitute it for h in my surface area equation. So let's take this, solve it for h. So this will come out to be 100 over pi r squared. And now we're going to use this expression to replace it with, to replace the h with. So I'm going to get 2 pi r, and then my new expression for h, which is 100 over pi r squared. Now here I can see that I can easily simplify. The 2 pi's will cancel each other out. One of the r's will go away, and I can multiply 2 by 100 to get 200 over r as my final answer. So this is a fairly easy function here, actually. Okay, so this is how we deal with three-dimensional volumes. The other three-dimensional volumes that you'll see all the time in calculus are spheres as well as cones. So you might practice some questions with those. Let's take a look at another question that is taking a two-dimensional object, turning it into a three-dimensional one. We're constructing an open box from a rectangular 8 by 10 sheet of cardboard by cutting out identical squares of side x out of each corner and folding up the edges. We're asked to find the volume of the box in terms of that value x. So once again, the first thing to do is to draw out the picture. So I have a rectangular sheet of cardboard. Its dimensions are 8 by 10. I'm going to cut out identical squares of side x out of each corner. So from each corner, I'm going to cut out a little square like this of side length x. And each of these guys has side length x. Okay, so all of these little guys have side lengths x here. Excellent. What I would like to then imagine, and you really have to turn on your three-dimensional imagination, is that I am now folding along these seams. Okay, I've cut out these, they're not there anymore. I'm folding up along these seams, and I'm folding these sides up to form an actual box. Okay, so the box that would look something like this, a nice rectangular box. Okay, there. So my little x's here will turn into my little sides here, whereas this side would turn into this side, and this side will turn into this one. Okay? So you might actually want to try it with a piece of paper to really persuade yourself that that's what it looks like. We're asked to find the volume of the box in terms of x. We've introduced only one variable, so we won't have to solve for anything, but we will have to think of what volume is composed of then. Now, I'm going to get a rectangular box here, and so the volume is then length times width times height. Okay, so let's take a look at the length. As I mentioned, the length, for example, if we think that this is the length, will be formed by this side right here once the edges of the x's are folded up. Okay, so I need to figure out what is the length that has remained after I've cut out x. The whole thing was 10, and then we took out two little x's. So the length of this remaining portion is going to be 10 minus 2x. And this will be the length of my box, 10 minus 2x, times the width, and the same logic holds for the width. The width of the box will be this quantity here. The whole thing was 8, and then we took out two little x's, which means that this quantity will then be 8 minus 2x. So this would be my width times the height, which is formed by actually folding up these edges, so that will be x. Okay, and this is my entire expression for the volume of this box. It already only has one variable. We're asked to write it in terms of that variable, so we're done here. I can, of course, open up the brackets if you really want to, and you probably will for calculus to easier take a derivative off and everything else, but as an expression, you're for now done setting up this function. Let's take a look at the next one here. So we're told that Shane is building a rain shelter to store 250 cubic meters of lumber over the winter. The shelter is to have a back, two square sides, and a top. The sides of the shelter will all be made out of plastic that costs $5 per square meter, while the metal material for the roof costs $10 per square meter. We would like to express the cost of the shelter in terms of one variable. So here we're once again actually given the fact that we are free to choose whichever variable we're going to use if we have more than one. This is a lot of information in this problem, so let's just take it one step at a time. First, build a picture. So we are building a rain shelter that has a back, two square sides, and a top, so no front. So let's build a picture that will look reasonable. So I have two square sides. The top, I know that drawing in 3 dimension takes a little bit of practice, so be patient. If your picture does not look fantastic the very first time around, it's okay. Okay, so something like this and like that. Okay, so see, mine didn't really work out either, but that's okay. I hope it's pretty clear what the picture actually demonstrates here. So now, one thing I would like to point out on the picture right away is that the sides of the shelter have to be square. Okay, so if I'm assigning any variables right away, I would like to be very clear that these are x by x, and so are these. Okay, there's x's everywhere here. The length of it, though, here is not specified to be the same, so this is likely some other variable. Let's call it y. All right, now this is all the information up until this point here. Then we also know something about the cost, and that is that the sides of the shelter are not the same price as the roof of the shelter. And the price is given per square meter, which means that the price has something to do with surface area. Okay, so let's make this quick note here. And now let's try to come up with the algebraic expressions for everything that we're given and for everything that we want. So we are given that the shelter can store 250 cubic meters of lumber, which means that the volume of the inside is 250. So let's record that, 250. And the volume is, as before, of any rectangular prism like this is length times width times height. Okay, so you're multiplying all three dimensions together. And in this case, because the sides are square, you're going to get two x's. So it's going to be x times y. So x squared y. All right. And then we have to come up with the cost of the entire production. So the cost will then be split along the two different prices. One price is going to be for the sides, so side costs, and one cost is going to be for the roof, so roof costs. Okay, so what do we have here? However many meters squared we need per side construction, or for every square meter of side construction, every square meter after that will cost $5. So whatever surface area of the sides, we then need to multiply it by $5 to get the actual cost amount. So what are the sides here? So we have two lateral sides here, and there we have two squares. So I'm going to have x squared plus x squared. But I also have this back side that will also have to be counted as a side. It's not a roof, right? So the area of this back side, it's a rectangle, and I can notice that its dimensions are y and x. So the surface area will be xy. Okay? So if I have, for example, 3 square meters of all of the sides, each square meter is worth $5. So altogether it'll be worth 15. Now I have this many square meters of the material to be used up for the sides, and each square meter is $5, which means that I have to multiply this by 5. Okay? Plus, however much the roof costs. So the roof surface area, this is my roof, and I can see that it's also a rectangle with dimensions x and y. So the total surface area of the roof is xy, and each square meter of that is worth $10. So I have to multiply this whole thing by 10 now. Okay? Now let's see, I would like to express the cost in terms of one variable. Now I have x's and I have y's, so I'm going to have to solve that problem somehow. So let's take a look at the function for the volume that we haven't really utilized yet. It's expressed in terms of x and y here. So I can solve this equation for one of the variables and plug this into my cost function to replace it for it to be in terms of one variable only. I can choose whether to solve for x or to solve for y. And in this case, I can see that it will be easier to solve for y because x has a power of 2, but y does not. So since I am free to make that choice, I'm going to choose the variable that's easier to solve for, which is y, which will be 250 over x squared. I will now use this expression for y to replace every occurrence of y in my cost function here. So what am I going to get? I can simplify a little bit along the way, and that is the fact that 2x squared plus x squared here is 2x squared plus x times y. Now my y is this expression, so 250 over x squared all times 5 plus x times y again, so x times 250 over x squared times 10. Now, of course, you can see that you can simplify these expressions, and in fact, if you start opening up the brackets, you will notice that you can simplify this entire expression a lot further. So I encourage you to do that. But for now, our task is complete. We've expressed the cost of the shelter in terms of one variable only x. So far, these problems involved a lot of rectangles and some three-dimensional figures, as well as circles. Let's take a look at problems that involve triangles and what tools might we need to actually attack those. The first one, a 30-foot ladder is placed against the wall with its bottom x feet away from the wall. Find the vertical height along the wall from the ground to the top of the ladder in terms of x. So again, here our variables are given to us. Let's draw a picture and then label it with those variables. So what I have is a vertical wall. And of course, I have the ground level. And I have that a 30-foot ladder is placed against this wall. So something like this. Let's see what else am I given in this problem. First of all, it's a 30-foot ladder, so I know that this length is 30. And I also know that its bottom is x feet away from the wall. So I know that this length right here is actually x. I'm asked to find the vertical height h along the wall from the ground to the top of the ladder. And I'm asked to find this length in terms of x. Okay, so this is the length I am after in terms of x. Excellent. So once we have this picture, we have to think about what relationships can we come up with that connect x and h together. Now I have a right angle triangle, so there's quite a few things I can use. The simplest one probably being the Pythagoras theorem. And I can see that I can use that directly here. I know that the squares of the lengths of two sides add up to the square of the hypotenuse. So by Pythagoras theorem, I immediately have that 30 squared is equal to h squared plus x squared. And I'm asked to express h in terms of x. Well, this is good news because this equation only has two variables, so I can simply solve it for h. Okay, so from here, I have that h squared is 30 squared minus x squared, or that h is plus or minus square root of 30 squared minus x squared. Don't forget that we will always have the positive and the negative square roots. Now, of course, here, h represents the vertical height along the wall from the ground to the top of the ladder. So in this case, h is going to be positive. So we can make a note about the negative solution being inadmissible, but that doesn't mean that we don't include it to begin with. And then claim that, in fact, h has to be the positive square root in this case. Okay, so Pythagoras theorem comes in handy when you have a right angle triangle and know the lengths of two sides, or one of them is the variable you're trying to figure out. Let's see what other things can come up when we're working with triangles. Again, a very standard calculus problems. All of these are very standard calculus problems. A 6-foot tall man is x feet away from a 15-foot streetlight. Find the length L of his shadow as a function of x. As before, picture first. Now here, I strongly encourage you to be as least artistic as possible, because if you make actual pictures of a man and a streetlight, it might be hard to see the mathematical structure, such as shapes, geometric shapes behind those pictures. So if you can draw everything as sticks, that's perfect. So what I have, of course, is a ground level here. And then I have a street light somewhere that is 15-foot tall street light, so I can label that with that amount right away. And I also have a 6-foot man standing somewhere that is x feet away from the street light. So this length right here is x feet away. Okay, I'm asked to find the length of the shadow of the man. Now the shadow is cast, so the street light, of course, has the light right on top. So the one artistic thing that I will allow myself here is to draw a little light. See, I'm not very artistic, hence I actually appreciate not having to be in math. And it shines the light on the man, forming his shadow on the ground. Okay, so I can actually draw this side as well. And this is now where I'm beginning to see that I have some kind of triangular structure to this whole thing. The length of his shadow is actually also given to me as a variable, so this will be L. These are going to be my two variables. So now I am asked to find the length of his shadow L as a function of x, which is his distance away from the streetlight. Looking at this picture here, I can see that, for example, Pythagoras is not going to be terribly useful because I have two triangles that are in operation. I have a triangle that involves the streetlight, and I have a triangle that involves a man. And two triangles, if we look at them closely enough, we can see that they're both right angle triangles, but also they both share this angle. Right? That's common to both of them. And because they're right angle triangles, that also means that these other two angles are equal as well. So these triangles are similar. Similar triangles are another really important tool to remember in these application problems. Similar triangles mean that I can write down the proportions between the sides of them. So let's think about what we want to do. So maybe let's call this side vertical side, and the side that involves the variables a horizontal side. Okay, so I'm going to write down the proportions between the vertical sides of each triangle and the horizontal. So in the big triangle, what do we have? The vertical side is 15. I can see that. And the horizontal side is this entire length, which is composed of x and then L. So I can label that because I'm going to need this. This whole length is x plus L. So the horizontal side in my big triangle is x plus L. Now I'm going to write down the exact same proportion for the small triangle, and because they're similar, these proportions have to be the same. You just have to make sure you keep the actual sides in the same way. So the vertical in the small triangle is 6, and the horizontal in the small triangle is L. Excellent. So now I have this relationship that ties together x and L. I'm asked to find the length L as a function of x, so that just means that I'm going to have to rewrite this to have the form L equals something. Okay, now these are two fractions. I can cross multiply to get rid of denominators, so I'm going to get 15L equals to 6x plus L. I can then expand the brackets, so 15L is 6x plus 6L. I can then move all the L's onto one side and all the X's onto the other. So I'm going to get 9L equals to 6x, which will then give me that L is equal to 6/9 or 2/3 of x. Okay, and this is going to be my final expression. I've written L as the function of x. Great. So similar triangles is another really good technique. Let's take a look at what else we have in store for us here. A rocket flies off vertically from its base and is being followed by a camera set up on the ground 2 kilometers away from the launching site. Find a relationship between the height of a rocket and the angle of elevation of the camera. So this right here is already telling us that we will likely have to use some kind of trigonometry because we now have to involve angles in our consideration of triangle. Notice that in the two problems before, there was no talk of an angle at all. So we knew we could get away with either Pythagoras or similar triangles. Here is where we would likely have to introduce some kind of trigonometric function. Now let's again start off by simply drawing a picture. So I have the ground level and I have a rocket that flies off vertically from the base, and I also have a camera somewhere on the ground. So let's say this is where my camera is. Here is my interpretation of the camera, and this is where the rocket flies off at height h at. Okay, so here's my rocket. There we go. This is the best I can do in terms of pictures. So as the rocket increases in height, the angle of elevation, which means between the ground and how the camera has to now point, increases. So I have to think about the angle that connects the camera and the rocket, which it's filming. And now we can clearly see our triangle. Let's label it. So I know that the camera is 2 kilometers away from the launching site. I also know that the rocket is going to be at some height, but I don't know what the height is when I want to measure that angle, so let's call it h. And I also don't really know what the angle is, so let's call it something. Let's say theta. Okay, so what I have now is a triangle where I have the angle, I have the opposite side, and I have the adjacent side. Of course, I can use Pythagoras to calculate the remaining side of a right angle triangle, but I might as well use the quantities that I already have labeled. So what trigonometric function uses from the point of view of the angle the adjacent side and the opposite? Well, that's tangent, right? So I can write down the expression for the tangent of theta. Tangent of theta is the opposite side in the triangle, which is h here, over the adjacent, which in this case is 2. And this right there is a relationship between the height of a rocket and the angle of elevation of the camera. Okay, once again, in calculus, you'll take this one step further and actually talk about the rate of change between the rocket flying off and the angle increasing as it takes off. For our last problem here, we will combine a few things that we've already seen. So let's take a look. A crocodile is stalking a zebra located 20 meters upstream on the opposite side of the river of width 5 meters. So notice that that's the one piece of information that's not yet present on the picture. The width of the river is 5 meters. So this width right here is 5. Okay? What do we have? The crocodile can swim at 1 meter per second and run at 60 centimeters per second on land. So it can swim faster than it can run. Assume the zebra does not move. Express the time it will take the croc to get to zebra as a function of x as labeled in the picture. So I have x here. So this x actually signifies the behavior of the crocodile. The crocodile, if the zebra is not moving, has to decide what is more efficient, to swim across and then run, or to swim directly for the zebra, or to do something in between, such as swim some amount of time diagonally and then run toward the zebra. These types of problems are very popular in things like even building underground pipes. Underwater or along the land, costs are different. And so you have to decide what is more optimal, to build longer underwater that might cost more, or longer on the ground that might cost less but might increase the overall length of the pipe. Now here I am given the velocity or speed of the crocodile. I am also given the distances that he has to swim or run, or I can figure those out. And I am asked to express the time that it will take the crocodile to get to zebra, which means that I have to come up with a relationship that ties together time, distance, and speed. So either from real life, where you recognize that the speed is measured in kilometers per hour and therefore is distance over time, or from physics courses that you've taken, we can derive that the relationship between the time is in distance and speed is as such. Time is distance divided by speed. Okay, so now the total time that it will take the crocodile to get to zebra is of course the time that he has to swim, if at all, and then the time that he has to run on the other side of the river, if at all. So total time is going to be divided into time in water and then plus time on land. Now each one of these has to then be expressed in distance in water divided by speed in water, and then correspondingly distance on land divided by speed on land. Okay, so what is the distance that the croc has to swim in water? The width of the river is 5. The distance that he has to swim in water is the length here, okay, which we do not yet have expressed fully in terms of the things that we know. So let's take a look at this triangle and recognize that this is just a right angle triangle, so we can apply the Pythagoras theorem to it. So the length of this side is the length of the hypotenuse, which will be the positive square root of 5 squared plus x squared. Okay, so this is the distance that the crocodile has to then swim in water. 5 squared plus x squared. And to get to time in water, we have to then divide by the speed in water, which is given to us as 1 meter per second. So 1 meter per second here. Plus the time on land, which is this distance right here. So this is also not yet quite given to us. We have to figure it out. Notice that the whole distance is 20 and this distance is x, which means that the remaining distance here is 20 minus x, and that is the time on land, divided by the speed on land, which is 60 centimeters per second. Now notice that everything else is given to us in meters, which means that we have to turn this measurement into meters as well. So 60 centimeters is 0.6 meters per second, and this is the speed that I'm going to be dividing by. Okay, and that's it. We've expressed the time that it will take the crocodile to get to zebra by swimming and then running if he decides to leave the water at this particular point. In calculus, you will then explore what exactly should this length x be in order for the crocodile to be most efficient in his hunting. These are all different types of applications and optimizations problems that you will see in calculus. I strongly encourage you to take a look at Web Work Assignment Module 6D, as well as a number of different application examples at the end of this section to see the most standard calculus problems that will come up in calculus. These are really good starters, and you guys will develop further and more deep applications once you are in your calculus courses.